Welcome, everyone. Good morning, good afternoon, good evening, depending on where you're joining us from. My name is Carl Lewis, Senior Director of Partnerships at LandingAI. Delighted to be joined by Thomas Reitberger, Product Manager at Micro-Epsilon. LandingAI and Micro-Epsilon has been collaborating with each other for the past few years, helping companies solve the most challenging inspection and defect detection projects, combining imaging hardware from Micro-Epsilon and powerful vision AI models from LandingAI. Trust you'll find this session useful, enjoyable, and insightful. If you have any questions, make sure to add them to the chat, and we'll address them as we go, or there's actually time at the end. So today's session, here's a little bit of the agenda. Thomas is going to start by introducing some EV battery use cases. He'll also do a demo, hand the baton over to me, and I'll give an intro to LandingAI, what our focus is, and some of the unique differentiated technology that we have, including platform learning lens and also large vision models. I'll conclude that with a demo. So before we get kicked off, just want to add a little bit of context and set the stage as to why LandingAI and Micro-Epsilon partners on projects. From a personal perspective, I've been working in vision for almost 30 years, worked on different applications in multiple industries. And really the key is starting with good image data, and especially in the EV industry, lots of really challenging imaging problems to solve. So Micro-Epsilon offers the largest range of displacement sensors to solve those challenging applications where you may have, a lot of reflection. So getting a good set of images is really important for creation of visual AI models, which is where LandingAI comes in. So we can take those 2D images and transform them into powerful models, and then getting those models into production and doing that super fast. So really accelerating that project development, deployment, and that time to value, and making sure that you're able to produce a product that has exceptional quality. So with that, I'll hand over to Thomas.
Yeah. So also warm welcome from my side. It's a great pleasure for me to having the opportunity to present at first place Micro-Epsilon, and also our sensor tools, which we have in place and which we are using to generate the images Carl has already talked about. And I am a product manager for Micro-Epsilon 4 years now, and I'm responsible for a sensor called reflect control sensor, which is quite special because it can measure in direct reflection and on shiny surfaces, transparent materials, glass, and we will have a look at the sensor in detail. So perhaps for those of you who don't really yet know Micro-Epsilon, I also prepared a few slides to get you a little bit into it. And first of all, we are located in Germany. So most of the company and also our company group are located in Germany. We stand for sensor systems and solutions, and also we could do some customer-specific solutions if they are needed. And we think mainly our goal is quality, efficiency, and innovation based on what we call more precision. So the company itself exists now for more than 50 years. And as I said before, the slogan for us is more precision. And we do this by a lot of sensor systems. And then we also will have a quick look at our portfolio here. And nowadays we are more than 1,700 employees worldwide. And also have over 2 million euro in turnover here. So perhaps more exciting for you is also the product range we have. So as Carl said, it's one of the brightest product ranges in the market. So it begins with laser triangulation systems. We also have confocal chromatic systems, white light interferometer. We can have capacitive sensors, eddy current sensors, inductive, magneto-inductive sensors, draw wires. But even when it comes to 2D, 3D laser scanners, we have them in the portfolio. The 3D snapshot sensor, which one of them will be the focus today. And we can even build up measuring systems, so whole systems where our sensors are integrated if it comes to bigger projects. And we have optical micrometer, fiber optic sensors, color sensors, thermal imager and pyrometer, and also laser distance sensor. So as you see, the portfolio is really a wide range here. And but we want to focus then today on the EV battery production. So here is just an overview of some projects we are in, and the industries we are mostly in is the semiconductor industry. Then we also are in automotive and aerospace and machine building, and also in other industries, of course. So we want to focus on the EV battery today. So for us, the production of the battery foil is a crucial thing. And here we have different sensors in the portfolio which could help you solve your measurement problem. Beginning at a thickness measurement of the foil done by two-sided, we do it convocally. And we could also measure the gap between two shiny rollers. And this is done with a special sensor to be especially designed for the roller mapping. Then we could also have a look at the drying behavior based on a pyrometer sensor. We can measure the heavy edge on both sides. So when the foil is applied here, there is often a problem that it isn't applied that perfectly. And we could also have a look with our 2D sensors here. And it is also possible to do a one-sided thickness measurement on the active material, or measure the thickness of the anode or cathode material, here done with a point sensor. So we have a look at the whole production process shown here. And for us, it begins with the mixing. And it's just that we have solutions in this case. And the coding, where we have several projects where we are in. Then the drying process, which is controlled. Then the calendaring with several projects, and also the cutting, the assembling, and then also the forming of the battery itself. And also in the last step here, in the packaging, we can also have a look at the packaging. So the main focus for us today is the reflect control sensor. And as I said, it is designed especially to measure on high reflective surfaces. So especially in the EV production, we will see some examples where you can use the reflect control sensor in. And we call the measurement principle here the so-called phase shifting deflectometry. So what is phase shifting deflectometry? So here on the right-hand side, you can have a look at the sensor from a little bit below. And as you see, you have a screen and you have two cameras. Then you put your reflective surface below, and on the screen, a sign pattern is projected to the surface. Then it is possible for the cameras to see the direct reflection of the reflective surface and transfer this into a camera image. By doing so, you have the opportunity to, on the one hand, generate 2D images, which we will have a look at, which are an important thing for us, that LandingAI has the opportunity to get really the defects out of it. And also we can calculate the 3D point cloud. So how the results are generated. And on top of the right-hand side, you see the projections we are doing to the target. So the sign pattern is projected at least 4 times to the target, 2 times in horizontal, 2 times in vertical direction. And by overlapping these images, we have the opportunity to generate 2D images. We call them amplitude and curvature image, and also calculate a 3D point cloud. So approximately a recording time for the sensor is about 2 seconds. So in these 2 seconds, the sensor and also the target have to stand still. And after this, you can move your next target below the sensor and do the next measurement. And the processing time, which comes afterwards, is about 3 seconds. So to have one complete measurement and also the 3D point cloud and the 2D information, it is about roughly 5 seconds, always depending on how many projections you want to have and also on which data processing you will need. So let's have a look at the first example and also what the 2D images do for us. On the top, you could see an example of a battery pack. So one which could be integrated into a car, for example. And in the first place, our sensor generates a base intensity image. In this base intensity image, the brightness of the object is represented, and you could see, for example, color deviations. This is more or less what you get from a normal camera. So with our sensor, you can also get rid of a normal camera solution here. More interesting is when it comes to the amplitude image, because the amplitude image now represents the reflectivity of the object. So here, everything is highlighted, which changes the surface reflectivity. For example, a fingerprint and also the scratches can be seen a little bit better. And in the last step, we also get a curvature image of the surface. And in this curvature image, we can see any kind of bumps and scratches and stuff like that. It's more or less anything which changes the surface normal. So as you see here, some minor defects or the scratches inside. So the next example I've brought is a pouch cell, and we will also have a look at a live measurement on a pouch cell afterwards. But to begin here, as we said before, the base intensity image, so more or less the normal camera image you get. More interesting when we come to the amplitude image, where the customers can see these deviations of reflectivity. And most of the time they are excited about the curvature image, because here every scratch, defect, and yeah, any surface impact can be seen. But you can also have a look at 3D shaped surfaces. Like in this case, we would have a look at a shiny roller, and we would also get our base intensity image, our amplitude image here, and at last, our curvature image. So just for you to get some further applications in mind and see what the sensor is also capable of, I brought some extra examples. So in this example, it was parking distance sensors. The parking distance sensors, the small round sensors you have in front and the back of your car, also could have some defects in the production. So with the sensor, you can see minor inclusions or even the orange peel, which can be on top of them. You can also do measurements on glass. And in this case, we did a pattern recognition of an imprinted glass. And there the customer could see also if the pattern is formed right. Another example from is a glass watch. And here, a small scratch, and it's really only a nanometer scratch, goes from the right end to the top, and this made it a scrap part for this customer here. And the last example I want to show you would be a molded plastic for a car sensor. Actually, it's the molded plastic for a rain sensor, which is in front of your car. And if it would be polluted as this, then your rain sensor wouldn't work correctly anymore. So this is so far which I want to show you when it comes to the 2D images. But as I said before, it is also possible to calculate the 3D point cloud. And also in a lot of cases, the 3D point cloud is important for the customer, especially in semiconductor industry. This is an example of a wafer. It looks worse than it is. We are only talking of 7 microns from the highest to the lowest point. But in this case, our customer said he needed to have the wafer flatness below 5 microns. So this would be a scrap part. And what you also can see here is what the sensor is capable of, because even these minor defects can be seen in the 3D point cloud. Another interesting example for us is the shaping and dimension of smartphones. So today the smartphone backsides and also the front sides are very shiny, and this makes it for us possible to do a measurement based on the 2D data for seeing the defects, and also 3D point cloud for having a look at the shaping and dimensional accuracy. And the last exciting example which we had here was in aircraft industry. You can see here a part with a honeycomb material inside, and then a pre-preg material which is brought to the top, and then in a baking process it's formed out. And inside this baking process, there might be a damage to the honeycomb. And as you see here, there are 2 areas where the honeycomb has a defect. And this could also be seen and measured in the 3D point cloud. So now you might think, okay, normally if I have a shiny surface or a glass or a transparent material, I could just go and use a confocal sensor. And you're right, you can do this. And for this, we tried to do a measurement with a confocal sensor and our deflectometry sensor, and put the images next to each other. And what you see here is a polished slab which has a dent inside a dent. And on the left-hand side, you see with the point-to-point sensor to have the whole surface covered of 30 millimeter to 30 millimeter field of view, you would need about half an hour. On the right-hand side, you will see the deflectometry result, which you get in about 5 seconds. So this is a massive time saving you can have here. And as you also see, the quality of the result is very comparable. And if you go one step further, you could also say, okay, but I could use an interferometer for these measurement tasks also. And yes, of course, you can do so. But on the one side, if you just use a point interferometer, you will have the time problem. And if you have an interferometer which can cover a bigger surface, normally also the preparation and the setup for this measurement will take a long time. You see here a result which is done with a point interferometer from us, and also covering a bigger surface. It's a telescopic mirror, which we had a look at here. And if you look at the difference between the deflectometry and the interferometry result, you will quickly see that there is 50 nanometer difference. So this is, in most cases, more than enough to do it with the deflectometry. So at the moment, we have 2 products when it comes to the reflect control. On the one side, we have the 2D reflect control, which has a measurement area of 110 to 245 millimeter. This is the area which can be covered with one shot. And this sensor is only capable of doing the 2D images. So you get the base intensity image, the amplitude and the curvature image out of it. And on the other side, we have the 3D sensor, which has a little bit different measurement area, which we say is about 170 to 160. But as you see, it's a little bit trapezoid, but this is because of the cameras. They need to look on top of each other, and so this field of view is formed by it. So now just a quick overview of the sensor. What is the outstanding features the sensor has here? It's the repeatability, which is up to 1 micron. In most cases, it's in nanometer range. We have a set resolution, which is beginning at 10 nanometer. We have with the 3D Inspect software, and when I show you the live demonstration here, I will also have a look at the 3D Inspect software, a quick look. And compared to most other sensors which could be used, you have a massive time saving, up to 99% here. What you get is up to 3 to 5 million data points directly out of the sensor, 3D data. And we have also an extensive software development kit. So if you want to do the solution on your own and you're using Python or C++ and stuff like that, then you could just take the sensor as a raw data sensor and write your own solution. And also, all of our 2D, 3D sensors have an open standard when it comes to the camera image. So we use the GigaVision GanyCam standard, and for this, it's most of the time quite easy for an integrator to get the image and do the next steps with it. So to summarize here, when a 3D point cloud is needed, Micro-Epsilon already has an outstanding software for calculating for calculations on the 3D point cloud. But for us, LandingAI is such an important partner because all the 2D images which I showed you can be taken by the sensor and are really impressive, and you see a lot of stuff there, but we don't have a solution to say where you have a defect and how big it is. And in these cases, we always knock at Carl's door and then say, oh, here is our problem. Carl, can you help us? So much for the presentation from the Reflect control, or also a short overview. And if you have any questions after that, please also feel free to ask about. And I would now switch to my live presentation, which I also have in the back, and show you a live measurement on a pouch cell, which I now have under the sensor, which stands next to me. So we are now inside our 3D Inspect software, and we are inside the display image data. So what you see here is the live view, and I can also put my hand below, so you can now hopefully see my hand, and I can also turn it a little bit and stuff like that. And what I have to do now inside our measurement system is just in the first place, put the object in the middle of both cameras, and the pouch cell is packed inside here. So this is the area which I'm interested in. Then I can adjust the exposure time to the best I need for an image here, and I could do some further settings. And then I have the opportunity to go, for example, to the 2D images and start a measurement here. And on the left-hand side, you can also see how long the sensor needs to do an image. Then it is reconstructed here. And what you now get from us, as we've seen in the slides, is the base intensity image. So more or less the camera image. I could also scroll in a little bit and have the defects shown a little bit better. We get an amplitude image where we can also see all kind of scratches, defects, some minor dents and stuff like that. And I could also have a look at the curvature image where I can go inside and also see many impacts, minor impacts, which probably won't be a failure, but something like this would lead to a scrap part, as I think here in this place. So so much from that what I want to show you. What I would have to do now is just to save my images in in a format which then could now further be processed by Carl. And with this, I would hand over to you,
Just
Carl.
Thanks, Thomas. Just a quick question.
Yeah.
Maybe could you say a few words about trying to do the same inspection using a visible spectrum camera, not necessarily using deflectometry? What kind of images would you typically see?
I, I,
Um,
yeah, I would say here that our base intensity image is more or less what you get from a normal camera. So also in a normal camera solution, you could see some deviations here and perhaps some scratches if they are bigger. But if you would directly compare it to what comes out of our amplitude images, where all these minor defects are really highlighted. And I would even say so small scratches and small surface defects really can't be recognized by a normal camera solution here.
Sounds good. So just for our users, having those three types of images, you can really understand the kind of contrast you can achieve with your application. So then the next step would be, taking that image set into LandingAI's platform to
Yeah,
then build, a visual AI model, but having the flexibility of being able to select the right images that represent the best visible contrast is,
yeah.
is a big advantage over visible spectrum
You get the
cameras.
complete package here. Yeah.
Yep. Yep. Great. All right. So I think I'm up next. So I will share my screen. Um, so I will give an overview of LandingAI, and then I'll go into the demo, but actually take the images that Thomas created, and we'll take a look at the kind of models that we can build using LandingAI. So for those who are new to LandingAI, we help companies build, deploy, and scale visual AI solutions. We have a platform that is called Landing Lens, and it enables you to build a model quickly, iterate and deploy your visual AI solution quickly. So historically, users have had to iterate many times on a solution, perhaps using a rule-based vision library and getting the rule prescribed just right to be able to deal with the variation that's observed in an application. With LandingAI, we focus on domain-specific data sets that customers provide. So that could be a small domain-specific data set of images used in production, or it could be a much larger domain-specific data set and building a large vision model. So not a large vision model enables you to create a foundation model that understands the full variation in the application. So it could be hundreds of thousands, millions, billions of images. And because the foundation model understands the subjectivity and variation in the application, that can be built into the foundation model, and a few labels can be applied to fine tune the model, which means that you can extract the value a lot quicker than if you have to label those images one by one. So that really means the companies can gain intelligence from the vision data. Companies may have vision data, in a bucket somewhere, and we're enabling those customers to really extract that value a lot quicker than previously. So for us, it's all about enabling customers to build a model quickly, without prerequisites to be a data scientist or machine learning engineer. Generally takes a couple of hours to get trained on our platform, and then you can quickly build those models. So here are a few verticals that we're strong in. All of these verticals has vision data that customers want to extract information from. So it could be a semiconductor wafer or imagery from drones that are inspecting electrical infrastructure, power lines. We have models deployed for customers to extract value. Okay, so a little bit of introduction to Landing Lens. Landing Lens building blocks are in three buckets. So the first bucket is data management. So the first thing you think about is getting that good data. So Thomas created that image set, and the next step is really cleaning the data, make sure it's labeled correctly. We have those labeling tools where you can work with a team to build consensus on your labels. The second bucket is training those models. You have the option to look at model performance, compare, analyze, optimize, all within the platform without writing any code. And our platform really streamlines that iteration. Very user-friendly. No code is needed, and the objective here is to build that high-performing model as quickly as possible and get into production. So on the deployment side of things, once you have that model trained and ready to go, it's then all about how you want to deploy. So it could be that if it's a drone application, you may want to create a cloud endpoint, or you may want to, have the model running on the edge. If it's in a production line, say in an EV factory, it could be that you put the edge device next to the production line in a cabinet using our Landing Edge deployment app. And all of those deployments are effectively managed from one location. Okay, so here are some generic tasks that we have for each of our models, and they're broken down into specific classes. Defect detection classification. So taking Thomas's images, we can detect specific defects. It could be fingerprints, it could be scratches, it could be protrusions, but we really need those high quality images with good visible contrast to be able to detect those defects. Or it could be that we just want to classify good and bad. Maybe we have images already labeled and we want a model to tell us whether an object is good or bad and provide that prediction. Maybe you want to stop a line, or maybe you want a robot to pick the pouch off the line and put it into reject bin. Another could be scene analysis. The one thing that ties all these different things together is the images. So we take those images and then we decide, what task is needed. So it could be that we're verifying that an object has been assembled correctly. Maybe it's there's lots of different objects that's contained in the kit, for example, in this case. Or we may want to detect a object in a scene. Or it could be that we have multiple defect classes in a scene. It could be that we have 10, 20, 30, or 50 different types of object that we want to detect. And we have different classes of those objects that we want to detect. And when the model sees that specific class, we want to signal alarm. And the last OCR, where we're reading characters. So we may want to combine all of these different tasks together and give an overall result. Okay, so some challenges with adoption of enterprise AI. This is fairly ubiquitous. So usually what we see is customers do have the data, but it's unstructured. There may be many, many images in a repository somewhere and also videos, but there's no structure to it. There's no labels, there's no metadata associated with it. It could be that customers, are adding many more images, many more part inspections that they want to do, and the complexity, is increasing. So as customers deploy AI solutions, it could be that the models that are created are not keeping up with the application design. Another third challenge is development is very time consuming. A lot of data labeling, a lot of training, deploying models has historically taken many months, and models have needed to be retrained as subjectivity increases. And then the last is projects stuck in POC. So this has happened quite often where a project, because maybe the customer doesn't really understand the subjectivity in the application, it remains in POC because many more images are needed to understand the subjectivity to optimize the performance of the model. But there is an answer to all this, and LandingAI has unique technology to solve these problems. So unlike language models, LLMs, vision models aren't all equal. So with vision-based models, our LVMs, we're actually using customers' data to train foundation models. So it's absolutely true. There are generic LVMs out there that scrapes the internet for many, many images. But what do you have left? What you have left are customer images that are domain specific. It could be that you have many, many images. It could be millions of images of battery pouches, as an example. And we create a foundation model that understands the subjectivity and variation in the application. And because it's done over so many images, we take that foundation model, which is unlabeled, so it's semi-supervised learning, and we're able to apply a few labels. And because the foundation model has looked at each image and understood all of the different features and how they relate to each other, we can then create a LVM, which provides an increase in performance compared to a generic LVM, and a lot less time labeling imaging data. So just to reinforce that point, so we take the domain images, the data set that you can see on the left. These are unlabeled, so self-supervised learning, no labeling required. We build that foundation model. We fine-tune with a few labels. And then on the right-hand side, you can see, then we can start classifying based on that LVM. We can start getting predictions, but we can also label more images as well using vision-based RAG. So which images are similar? And because we have that inherent learning inside the LVM, we can then build a fine-tuned model inside our Landing Lens platform. Okay. So again, like I mentioned, there's a couple of things here which are really interesting. One is better for performance, because we've learned that subjectivity that occurs over time using many images, millions, billions of images, that enables to increase performance compared to a generic LVM. Remember, we're using domain-specific images. It's also lower effort because we're training a foundation model using customer-supplied images. There's no labeling needed. So, we we don't need to label every single image. So that translates to many millions of dollars in savings and return, based on the number of images that you see there. Okay, and then just one last thing regarding LVMs. This is really interesting in terms of how long it takes to deploy a project. So typically, you would see an application requiring many weeks of iteration. Just going through the images, maybe relabeling, fine-tuning everything. What do you see with an LVM? Because you're just tuning with a few labels, that development time now is significantly reduced, which means you can get the project into production a lot sooner. Okay, so I'm gonna start with a little bit of an intro into our platform. Okay, so let me start by talking about Landing Lens. So Landing Lens is the name of our computer vision platform. Here you can build projects very quickly and easily. So you can get access to Landing Lens. There's a free trial available on our website. You enter your email and you'll be able to do what I'm doing now. So the first step here is to create your project, and you will see a number of different project type. Object detection. So this is where we use bounding boxes around the defect that we want to label. So we may want to detect things like scratches, fingerprints, protrusions. The next is segmentation, where we're actually segmenting all the images, and maybe we're looking for pixel precision labeling, and we get a model as a mask of pixels as an output. Classification is where we are detecting good and bad. So we can upload already labeled images. And then visual prompting is where we use a paintbrush for labeling smaller areas in our image, and we segment different areas of our image. So I have a couple of projects here that I want to show everyone for EV inspection. And these are the images that Thomas uploaded to the Landing Lens org. So this is actually using a classification model, and all I did was I labeled the good and bad images. So you can see here obviously the difference between good and bad. I trained a model, and I was able to get really good precision and recall. So once I'm happy with the results, the next step here is to put it into production. So I have a choice of either setting up a cloud endpoint, or I can use our Landing Edge app. So in a factory, I would probably use an edge device if this is a move-in production line. So I would take the model from Landing Lens, and then I would put it onto an edge device and then present new images to the model that's on the edge device and get the prediction back. The other project I have here is actually using a laser displacement sensor, and this is inspection of a battery pack. And 1 second to refresh. So this is using a laser displacement sensor to scan a battery pack, looking at the topography of the battery. And what we get is a height map. So these colors represent the step change in the image. Can't really tell much here until I turn the heat map on. So the heat map will give me an indication of the specific pixels that were activated by the model. So you can see here, the model was very specific about these areas. So these areas actually translate to specific protrusions that could potentially be a weak spot and could potentially be a leak in this specific battery cell. A whole battery pack comprises of many of these cells. So the customer was concerned with specific battery cells being a weakness, which would drive the performance of the overall battery pack down. So again, this is a classification project where I've uploaded good images and bad images. I've trained a model, and the next step would be putting it into production, get it onto an edge device, and then showing new images to the model, and then getting prediction back. Okay, so let's talk a little bit more about deployment. Now, I mentioned there are a few options for deployment. We have a really easy and simple way to deploy a model in a few clicks. You can see here on the right, we have our different deployment options. We have a cloud-based API. We have LandingEdge, which is the name of our software app. And there's also a headless app, which is Docker container. So if you had your own interface that you wanted to create, that's fully flexible and available to you. So we get our images into an LVM. We build our domain-specific model. We deploy it, choose our endpoint, and then we create our continuous learning loop. So as we take more images, we can feed those images back into Landing Lens, and we can refine our model. That means our model performance is going to improve over time. It could be that the subjectivity applications are going to increase, but because we're getting more images in, the model can be retrained, and we can keep our performance of our model consistent. Okay, so benefits of building your domain-specific LVMs with LandingAI. So for us, it's all about understanding data, understanding your unlabeled images. As I say, those images do not need to be labeled. Self-supervised learning. We achieve higher accuracy with our domain-specific LVMs using domain-specific customer images, increasing accuracy for the vision application. We increase speed to production. We eliminate the need to build models from scratch, get customers up to target accuracy a lot sooner with less labeled data and effort. And then it's all about integration. How do we integrate with the customer's production line using LandingEdge, our software app for deployment on an edge device? So really accelerating that building and deployment process. Okay, so for those who are interested in consulting with LandingAI, we do have a no-cost consulting session that we can schedule. You can follow this link. The presentation will be made available, and you're more than welcome to schedule some time with one of our experts, and we can go through your project. We can make recommendations. We can also bring in Thomas and his team to review an application and figure out the best hardware and software mix for the project. Okay, I think Grace, that's you.
If you don't mind, go to the this is live. Thank you, Thomas and Carl, for the informative sessions. Now we will move to Q&A. I already see a couple of questions in Q&A button. So if you haven't had a chance to use ask question, feel free to ask question using Q&A button on your Zoom. I see one question. Maybe this is for Thomas. Is this possible to do the test measurement around the world, or do we have to send the sample to Germany, your office?
You are also always free to send samples to me, and we can do some test measurements in Germany. But of course, it is not necessary that you are located in Germany. So we have distributions all over the world, and they also most of them have the reflect control sensor, or I can send them over. And then most of the times, the easiest way is just to do first few tests with the sensors in place. If it comes to more difficult measurements, for example, then perhaps we can also do a short Teams meeting and I have a look at it from far away. So most of the times it's not necessary that you send the samples to Germany, but you're always free to do this, and then I will directly have a look at them, of course.
Great, thank you. Another question is, are you able to automatically detect some damage that product deemed unfit for commercial use or need replaced? Maybe it's a question to Carl or yeah.
Is that, just make sure I understand the question, is it a automated inspection? How do we include the technology in an automated solution? Did I hear that correctly?
I think it's more of a, yeah, how you can create the automatically detect some of the defects. So maybe if you can.
Oh, okay. Yeah. So we've worked on projects, Thomas and I, where reflect control sensor is mounted on a cobot, where the object, it could be in a fixture and the cobot does the inspection. We've also worked on projects where a vehicle comes into a fixed position and a big reflect control sensor is inspecting the whole vehicle for paint defects, that kind of thing. But more on the EV side, this can be integrated into an existing production line. We just need to understand space available, all the different controls and cycle times and those kind of things. So yeah, that's definitely possible.
Perhaps if I also say a word here, it's a fully automatically inspection, which is possible if we combine the sensor with the LandingAI process, and then we are also capable of just sending the result to the PLC. So just having the result via Ethernet, EtherCAT, Ethernet IP, whatever you want. And I think the main thing here is in an automated solution that we have time to take the images. So this is most of the time the crucial thing here, that we need the 1 to 3 seconds, as I told you, to do the measurement. And after that, the most of the things work in real time.
Great, thank you. Next question, regarding the training, LandingLens is capable of self-training, hence no need to produce lots of training images ourselves.
I think the question is referring to LVMs, and it sounds like the question was related to training a foundation model without specific labels. And yes, that's absolutely true. So foundation model looks for interrelationships between different features, and then creates those self-supervised training signals to build up an understanding of the full variation and subjectivity of the application in many, could be millions or billions of images. And then from those foundation models, we can fine tune with a few labels in LandingLens for the specific defects that we're interested in detecting. And that means that we don't need to spend our time labeling every single image. So that's where the time save is. And then the outcome of that is much higher accuracy than a generic LVM that scrapes the internet, but we're using domain-specific images supplied by the customer of their real application.
Great.
Hopefully that answers the question.
Yep. Thank you, Carl. Yeah, and also if you don't have a lot of images, we also offer pre-trained models. So you, without user needing a lot of images, you can also fine-tune your model out of pre-trained model. One additional question, is it also possible to measure on 3D shape surface? This question to Thomas.
Yes, this is a little bit hard to answer because I can't give you a detailed number about how the shaping of the 3D model has to be. But basically, it's possible. I've also added the example of the roller mapping, and it's also a shaped surface. But what you have to keep in mind here when it comes to the sensor is that we always need the direct reflection to recognize a signal. So the light which is coming from the display has to be captured by the cameras in a direct angle. And if this direct angle exists, then it's also possible to measure on a shaped surface or a little bit curved surface. But if you have a really bent and extreme 3D shaped surface, then you will lose the areas where you don't have the direct reflex anymore. So we call it shaded areas in this place. Yeah.
Right. Next question, can we deploy it in localization where no internet?
From the sensor side, this would be possible. So the sensor captures these images based on the software, which doesn't need internet. So you would do a parameter set on the sensor, save it to the sensor as some kind of cooking recipe, as we say, and then the sensor would do the tests or the things you want to see in an automated way, also without internet. But perhaps also UCall can do an offline solution here. Yeah.
Yeah. So if internet, let's say it's in a factory, the internet is unavailable, you can use LandingEdge, deploy it to edge device, download the model to the edge device, and you can use your edge device, which is air gapped, and you will just keep presenting images from the reflect control sensor, and it will keep giving you predictions. What you do lose is the ability to do the continuous learning aspect, but you can save those images offline. So you could save those images to the edge device or some other location, and then you could sync it with Landing Lens, when convenient, and then you can retrain the model that way. So yes, that is an option.
Great. One last question concerning time. How about the prediction time for each image in milliseconds, second, assuming the image size is about 2500 by 2000 pixel? Their production line required 300 milliseconds per image.
So
yeah, go on.
Then
sorry.
Then the sensor would have perhaps the problem here, because I think the software doesn't have a problem with this time. But as I said before, the sensor needs 1 to 3 seconds to do an image. So this is basically the bottleneck here. So a minimum of 1 second is needed for getting the image, or for getting one image set, as I would say. But Carl, you're quite much more faster than me.
Yeah, so I think benchmarking, I think we're up to 30 inferences a second with LandingEdge. So yeah, that's the benchmarking for inference on an edge device with LandingEdge. Yeah.
Thank you both. As Carl is showing on the screen, you can get started Landing Lens for free, and you can also join the community for any question we couldn't cover today, and you can also get the free foundation course for the computer vision. So with that, let's conclude our session. Thank you, Thomas and Carl, and everyone joining today's session.